Looking at all the trig functions, you can see that none of them pass the horizontal line test. It's all really because of the periodic behavior. So if we want to talk about inverses, we need to talk more specifically about restrictions of the domain, which is what mathematicians typically do when you want to work with inverses, uh, which is what you see when you're working with x squared. If we restrict the domain of x squared, which is this function here, right? This does not pass the horizontal line test, therefore it does not have an inverse. But if we restrict it to only the positive side, this does pass the horizontal line test. Therefore, the square root of x makes sense when you're talking about only the positive values of x. Now, instead of looking at the positive values, you could look at the negative values, and that way this does pass the vertical line, or sorry, the horizontal line test again, and that means the inverse of this function would actually be the negative square root, and gives you a completely different function. You have to consider each one of these things separately, though, because you cannot have a full inverse of the square root or of x squared, because the square root's not it'd be plus or minus the square root, and that's not a function. So now let's consider a sine of x and consider a similar scenario where we restrict the domain to look at what the inverse of sine could be. So this is sine of x, and we can see here that we have this periodic function, and of course does not pass the horizontal line test. Now, when we restrict the domain, however, we can see that there's really only two unique possibilities. We have this portion right here, and it's repeated again right here. Let me do it like in yellow. This portion, and it's repeated right here. It's also repeated back here. It's really the same shape. It's really this, as you go left to right, it's increasing, and that those all pass the horizontal line test, right? I can take a horizontal line anywhere in this yellow region of any one of these three, and it only crosses it once. And in addition to this, I could also use this region here, and this one, and this one. And of course, there's infinitely many of them. These also pass the horizontal line tests. And so the question then, is which one do we choose? And for a lot of the times, whenever you're working with trig functions, we really like to be in this first quadrant, this interval from 0 to 90 degrees, or pi over 2, because a lot of the good stuff that we like to think about trig is nice to work with in this quadrant. So we're going to choose, out of all of these angles, we're going to choose this one right here for our inverse function. Okay, now when we do that, you can notice that f of negative pi over 2 is sine of negative pi over 2, gives you negative 1. So this point is at negative pi over 2, and f of pi over 2, right, sine of pi over 2 is just positive 1. So this point is also there. So we have negative 1 and positive 1. Those are going to be our domain, what ends up being our domain for the new function. But it's important to note that those do equal each other. Like when we go from this interval from negative pi over 2 to pi over 2, we're including those two things. Therefore, the range on this one is going to be from negative 1 to 1. It does hit those endpoints. Now, this is going to be a common thing you're going to see in all the inverse functions for trig. Is we're going to see this arc word in front of it. That's because this inverse sign is the negative 1. So like, for instance, x to the negative 1 power is 1 over x. Depending on where the inverse sign is at, sine of x inverse is actually 1 over sine of x, which is the same thing as cosecant. whereas putting the negative right next to the sign, this is the sine inverse of x. It's a little confusing. That's the reason why there's this other notation, arc sine, that stands for the inverse of sine. So you could either see sine like this or arc sine, they're both the same thing. If you ever see this, however, this does not mean the inverse of sine. It means the reciprocal of sine. Okay. Now, the graph on the left here, this is the arc sine. You can see that we have this behavior, you know, it would continue on like this if it were the regular sine function, but this is not a function. So we had a restricted domain to negative pi over 2 to pi over 2, and that becomes our range, the inverse. And then our range of negative 1 to 1 becomes our domain, negative 1 to 1. So this is the inverse graph. If you had chosen different portion of the domain, like for instance, if we chose this one instead, then the inverse of this would be just this thing shifted up some. It'd be kind of up here if the graph were to continue, but it'd just be shifted up. It'd be the same shape, it'd just be shifted a little bit. If instead we chose a different period, like this, or a different portion, like this portion here, where it goes down like this, then that gets flipped up to be this shape. You can see that it's different shape than this one. It's actually a flipped version of it, and it's shifted up, you know, vertically, so that it's going to give you different values. But for a lot of the reasons, like, you know, that I told you before, we like to work in this domain 0 to pi over 2, and so we want to have this portion as our graph. Now we can do a similar process to both cosine and tangent, and when we do that, we're going to look, we want the 0 to pi over 2 again, and this is what we get for cosine. For the inverse, this is the arc cosine, as I've written here. And again, it goes from negative 1 to 1. That was the range from cosine, but now it becomes the domain for arc cosine. And 0 to pi is our range, or the domain of cosine. Tangent, on the other hand, tangent looks like, you know, on a quick graph, looks like this. And then, of course, it repeats this behavior over and over again. We only considered this first one, you know, again, for the same reasons. It's in that central angle. It has 0 to pi over 2 in there. And when you flip it, it's nice because it actually has a domain of everything. Because it goes downwards and upwards to positive infinity, negative infinity to positive infinity on the range. When you flip it, you get to negative infinity and positive infinity on the domain. And now the range is bounded between negative pi over 2 and pi over 2. Of course, at negative pi over 2 and pi over 2, tangent has asymptotes, which means that arctangent, which is what this one is, right? Arctangent will never reach these values. Okay, so when we're working with these inverse trig functions, we don't tend to work with the definitions because we can keep in mind what we're looking at. Like instead of working with arc cosine, we can work with the cosine. It's very similar to how sometimes when working with logarithms, it's easier to work with exponential functions. Well, a lot of times, instead of working with the inverse trig, it's better to work with just the trig functions. But you need to keep in mind the restricted domains. That's the important thing. So here we have arc cosine 1 over 2. Now, it's important to note that if this were to equal something, then we'd have 1 over 2 equals cosine x. And what we're talking about here is arc cosine of 1/2 is an angle, because you only put angles inside of trig functions. So arc cosine of 1/2 is going to be some angle that you get a result in. It's the same thing you get when you say cosine of theta, or cosine of some angle, equals 1/2. And for cosine, I showed you that before, the domain of arc cosine here is going to be, let's go back up here real quick, is going to be from 0 to pi. That's the angles we're looking at. We can't have anything greater than that or anything less than that. So when does cosine of some angle equal 1/2? Well, if you look at the unit circle, cosine is the x-coordinate. So the x-coordinate 1/2 is going to be here. And that really happens at either 60 degrees or negative 60 degrees, which is the same thing as if you go all the way around to 300 degrees. The same thing as pi over 3, negative pi over 3, or 5 pi over 3. So because we're restricted to the domain of arc cosine, or I should say the range of arc cosine in this case, we can only get the values of 1/2 from pi over 3 or 60 degrees. So this of course is the same answer, pi over 3 radians or 60 degrees. So that's our answer for arc cosine 1/2. Now sine inverse of root 2 over 2, this is the same thing as arc sine. Root 2 over 2. Looking at the unit circle, arc sine works in the negative pi over 2 to pi over 2. That's going to be this range right here, quadrants 1 and 4. But just looking at the unit circle, and we look at root 2 over 2 for the y value, right? The y value, root 2 over 2, something like here, I believe. It's not going to be down here at all because it's positive root 2 over 2. And this quadrant, this is really, in this quadrant, this is really this 45 degrees. That's when you get root 2 over 2 for a y value. And that's the same thing as, so you could say this equals x or theta, it doesn't matter. We can just say theta. Theta equals 45 degrees, which is the same thing as pi over 4. Now, of course, this is also a valid solution to this thing, to sine theta equaling root 2 over 2. This is of course at 3 pi over 4, or 135 degrees. The issue is that we didn't have sine of theta equals root 2 over 2. We had sine inverse equals, or sine inverse of root 2 over 2. And that's the difference. That's why we get this one solution. So for arctangent, we know we're in the restricted domain of negative pi over 2 to pi over 2. And this thing is equal to theta, which means that tangent of theta equals negative 1 over root 3. And theta has to be within this range. It can't equal negative pi over 2 or pi over 2. It has to be somewhere between those two endpoints. So what we could do is we could create a triangle of this, a reference triangle. Theta, and then we can use, right, this is y over x. If it's in this range here, it can't be in 0 to pi over 2 because 0 to pi over 2 has only positive values of tangent. So it has to be in the 0 to negative pi over 2. So this should actually be in the fourth quadrant. That's the only way we can get negative values of tangent on this restricted domain. With that the case, that means that y has to be negative and x can be root 3. And of course, we can use this Pythagorean theorem to find c. Doing that give us c squared equals 3 plus 1, 4. So c must equal 2. This is actually a 30, 60, 90 triangle because I recognize the side lengths. So because we had 1, root 3, and 2. So that tells me that 1 is opposite the theta. That means theta must be 30 degrees, or pi over 6. In this case, it's actually negative 30 degrees or negative pi over 6 because we had a negative angle. But that's how you can find these inverse trig functions. Okay, give it a try in number 1.